Okay, so I hope everybody is okay. So for this today, we'll be discuss about the diode characteristic curve. So as mentioned last time, we know that we bias the diode according to the need. So we have the forward and the reverse bias. So for diode characteristic curve, we can illustrate this one using our x and y axis. Okay, such that the values along the x-axis is actually the diode voltage, and the value in our y-axis is actually our diode current. As we all know, quadrant 1 has a positive values for x and a positive value for y. So therefore, this region now under quadrant 1 is what is known as the forward bias region, where the applied voltage across the diode is a positive voltage and the current that flows through it is a forward current, which is also a positive value of current. Also, recalling our analytic, we say that quadrant 3 will give us a value of a negative value of x and obviously a negative value for y. So in this case, when we talk about diodes, this simply means at this region or at this quadrant, we are applying a reverse voltage. Therefore, it will produce a reverse current or leakage current. So quadrant 3 is actually the quadrant for the reverse region. Now, what is the characteristic curve of our diode? So let me just discuss this one. If you have a diode, which is actually a silicon diode, if this is a silicon diode, in order for the charges to move across the junction, the PN junction, the barrier potential must be overcome. Say for instance, we have now here a diode which is bias for which we had applied a forward bias. So applying a voltage here, say for instance a voltage of 0.1 volt. What happens is the barrier potential should be 0.7. So the 0.1 volt source voltage is not enough to forward bias the diode, or it's not enough for the charges to be able to move across the junction. Increasing now the value, say for instance, we increase the value to 0.5 volts, or the voltage applied across your diode is increased to 0.5 volt. What happened is 0.5 volt is not enough if your diode is silicon, because the barrier potential needs to overcome is 0.7. So if we apply a 0.7 volt this time for the source, something happens. So say for instance, we apply now a 0.7 volts. So what happens is, so we applied a 0.1, charges doesn't move across the PN junction. We applied increasing the value to 0.5. So current is still, there is no flow of charges across the junction. Therefore, your ID is still 0. Increasing now the applied voltage to 0.7, something happens. There's a start up or a take off point. So the value of your current starts to increase. So meaning to say, if your diode current is now increasing at a point of applying a 0.7 volts, therefore meaning to say the charges across the PN junction are started to flow. If there is now the flow of charge across your junction, meaning to say there is now a flow of current across your diode. So the 0.7 volts will be 0.7 volts must be overcome in order to have a flow of charges across your diode. So overcoming that value of 0.7 will show an increase of value on your y-axis, or will show that there is a flow of charges across your diode. And this curve is what is known as the knee voltage. So this happens when we apply a forward bias. So region or quadrant 1 is actually the forward bias region for your diode. Another characteristic of your diode is when you apply a reverse bias, or meaning to say you are applying a negative voltage across your diode. So say for instance, this is my diode, right? So reverse bias will simply mean I am applying the negative terminal connected to the positive terminal of the diode, and the positive terminal is connected to the negative terminal of the diode. So this is an example of reverse bias. So from our previous discussion, the reverse bias will simply create depletion layer. So the depletion layer will simply provide us a harder time for the majority carrier to move across the junction. Okay? So meaning to say, if you apply now a negative voltage here, applying a negative voltage, the current that pass through the junction are only the minority carrier. So these current are so small, or they are sometimes known as the leakage current. They are sometimes known as the leakage current. And that's the reason why if you apply a voltage, a negative voltage, there you will see a very minimal amount of reverse current, or sometimes known as the leakage current. However, if you increase the source voltage to a higher value such that it reaches now the breakdown value, say for instance at this point, this is now the breakdown voltage, the highest negative voltage applied across the diode, something happened. So avalanche will occur, it will create free electrons and holes, therefore increasing the number of minority carriers. So with this high amount of reverse voltage will simply produce free electrons and holes, which will create now an increase, no? Applying a reverse breakdown voltage will simply produce a large amount of reverse current or reverse leakage current. Therefore, as a summary, quadrant 1 is the normal operation of your diode. You usually forward bias it, and if it is silicon, it starts charges starts to move at the junction when you applied 0.7 volts across your diode. However, if the diode is germanium, you will need a 0.3 volts in order to reach, or in order for the charges across the diode to move. And obviously, if you applied a forward voltage, therefore the current that flows across the diode is also the forward current. On the other way around, applying a reverse voltage, that simply means the negative terminal of your voltage is applied to the positive terminal, and the negative terminal is applied to the positive terminal. That will simply cause depletion layer. With the depletion layer, there are still carriers that moves across the junction, but it has a very minimum amount, and those are the minority carrier. Okay? So with this minority carrier, there is a very small amount, and it is also sometimes called as the leakage current. However, increasing the reverse voltage applied across the diode, you will reach the breakdown voltage. Breakdown voltage will have an avalanche effect that will cause bombardment of electrons, which will cause free electrons and more holes. And if that happens, there will be a rapid increase of reverse current. So at quadrant 3 tells us applying a reverse voltage across the diode will produce a very small amount of leakage current or reverse current. However, when you reach the maximum reverse voltage, that is the time that there will be a sharp increase of free electrons and holes due to the avalanche effect. Okay? Thank you.